Hi, welcome to Easy Calculus. In this video, I'll be doing definite integrals. Now, definite integrals are integrals where you have a start and end point. Let's call it a to b of some function f of x dx. Now, this is different from the indefinite integrals because those indefinite integrals had no numbers here. Now we have numbers. So a represents a number, b represents a number. And when you have a definite integral, you can think of it as the area underneath a graph. So, for example, if my graph looks like this, and this is A, right there, and B is over here, then the integral of f of x, and this function is f of x, then the integral between a and b is actually going to be the area underneath this curve, but above the axis. So from a to b, that's what the area will be, and that's what calculating this integral is actually going to give us, the actual area of that. Now let's say f of x looked something like this. And then we wanted the area from a to b, and a was right here, and b was here. Then it's still the area. You're going to get the area above the curve, above the x-axis here, the area below, so that's going to be negative, plus some positive amount. So it's really the area either above, under the curve, or above the curve, depending on where it is. So here it will be underneath the curve, here it's above the curve, but then you get a negative sign in here. So that's what a definite integral is. And the way we evaluate it is, we don't usually have to think about these areas until later on, so we get to the washers and disk of revolution and everything. But for now, I like to just think of these just to help me guess what the right answer should be. Alright, but our main tool to solve these integrals is something called the fundamental theorem of calculus, and that's FTC. And what the FTC says is, let f be an antiderivative of little f. So let capital F be an antiderivative of this function. Then the integral from a to b of f of x dx is going to be equal to capital F evaluated at b minus capital F evaluated at a. So the fundamental theorem of calculus is, if you're given this, some function is integral, if you can find an antiderivative of it, and you evaluate the antiderivative at the two endpoints. You're going to do the top endpoint minus the bottom endpoint. That's how we're going to be solving all our definite integrals. Alright, so that's the first thing. This is the most powerful tool. This is number one, the FTC fundamental theorem of calculus. Now the next tool we're going to use is called, there's no name for it, but it resembles what we did earlier. Let's say we have a function, this is the sum rule. Let's say you have f of x plus g of x, and this is all in dx. Well, this can be split up. It's just, this is equal, this is number two. These are just identities I'm giving you. So number one was the fundamental theorem of calculus. This one is the addition rule. So if you have them together being added, you can easily split them up to get this plus integral from a to b of g of x dx. So these two are equal. That's the second identity you have. Okay? Alright. Now the third one I'm going to give you is easy to see graphically. So basically the integral from a to c of f of x equals integral from a to b of f of x plus dx. You need your dx's, plus the integral from b to c of f of x dx. Alright, and a is less than b is less than c. So basically what's happened is we have some graph like this, and A is the smallest one right here. B is somewhere in the middle, and C is all the way out here. So if I want the area underneath the curve for this entire thing from A to C, this is C, from A to C, instead of evaluating the entire integral, I can split it up. Instead of going from A to C, I can go from A to B, get this area, and then get the area from B to C, and add them up. And if I add these, I'll get from A to C. And graphically, you can see that, because all we're talking about is area. So that's the third one. This works with addition and with subtraction. This works with addition. Now the previous one, the sum formula, it also doubles for subtraction as well. Alright, so the next integral, the next identity we're going to use is this. Integral from A to A of f of x dx equals to 0. And the reason for this is an area. And from A to A is the length of the base, and f of x is the height of the function. So here, if we're going from A to B, okay, we have some base. Here from A to B we have base, from B to C there's base. But if you go from A to A, then the width of that is 0. So it's sort of like saying 0 times the height of that function, which is f of x at that point. So it's really, there's no, you're doing a rectangle, the area of a rectangle, and this is 0, and then this is some height. Well, the area of this is 0 times the height, which is equal to 0. So that's why if you have an integral from the same start point to the same end point, it's going to be equal to 0. Based on this idea of getting the area. And lastly we have this one. So we have the integral from A to B. That's just equal to, if we're going to go from A to B and we want to switch it, it's the same as integral from B to A, but with a minus sign. So we switch the endpoints, but we have to put a minus sign, f of x dx. Okay, so these are the tools we have to work with definite integrals. But the biggest tool we have is the fundamental theorem of calculus. That's just saying find the antiderivative and then plug in the endpoints and evaluate. Okay, so let me do the first example. The integral from 2 to 8 of 5 dx. Okay, so now 5 is just a constant. It's a coefficient. Well, it's a constant. And what that means, if f of x equals to 5, f of x equals to 5. That's the same as saying y equals to 5. So let's graph that. So 5 would be like up here. And 2 to 8, 1, 2, 3, 4, 5, 6, 7, 8. So this is the graph of f of x equals 5. Just a straight line at 5. Doesn't change at all. And we're going from 2 to 8. So this is from 2 right here to 3, 4, 5, 6, 8 to 8. So we've got to get this area between 2 and 8. So using middle school math, the area of this rectangle is base times height. So this base is the length of it is actually 6. Because it goes from start to 2, goes to 8, that's 6. And the height is going to be 5, that we know. So the area should be equal to 5 times 6, which is 30. So when we integrate this, we should get 30, or else we messed up. So let's do it. So using the fundamental theorem of calculus, the integral of this is just going to be 5x. And now, when I took the antiderivative of the inside, I get 5x, because if I differentiate 5x, I get 5. But now I need to put my endpoints, because I can't forget about them. Now I'm going to put this line, this is the standard notation to show your endpoints. And endpoints are from 2 to 8. 2 to 8. So this is equal to this. F of x valued at 2 to 8. Now we need to plug in these two values for x and subtract them. So it's going to be 5 times 8 minus 5 times 2. So I plugged in the 8 and I subtracted 5 times 2 from it. So this is going to be 40 minus 10, which equals to 30. So our answer is 30, and that's what our first assumption was. So now when I do these problems, I like to just check beforehand what the answer should be. Just a rough estimate. this was a nice problem. I could get 30 easily. Sometimes you might have triangles or funny shapes, but it's good to estimate the area. That way when you get your answer, you say, okay, that's reasonable. But this is right on the money as it should be. So that's number one. I'm going to write up the other examples so you can try them before I get to them. You see what's coming next to see if there's anything you can learn from this video, or if you already know it. Alright, these are the examples I'll be covering in this video, and I'll just be walking you through all of them. So let's get to the first two. Alright, so you're welcome to try them before I do, just to see if you can get them right, and you can check to see how I did it, to compare the methods. Okay, so now we have the integral from 0 to 6 of 2x dx. I'm going to do this, keep my endpoints, my limits of integration, pull the 2 outside, I'm going to get x dx. Now this exponent of x is 1, so I need to add 1 to that to make it 2, and then divide the whole thing by 2, because that's the new exponent. And so this is going to be 2 from x squared over 2, evaluated from 0 to 6, so I need to keep that. Now I can simplify these two, so this is just going to be x squared evaluated from 6 to 0. Okay? And so what I get is 6 squared minus 0 squared, which equals 36. So that's my answer for that problem. Now let's see if that makes any sense at all. Because we're talking about area, so it should be able to draw it. This is just a slope of 2. So this function is saying y equals 2x. We can easily graph that. So at 0, 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay. So at 0, it's 0. At 1, it's 2. 2, it's 4. 3, it's 6. So basically our graph is going to look like this, and it's going to keep going. We care about from 0 to 6, so that's where our limits of integration are. So this is what we care about. We need to find the area of this. Well, the formula, this is a triangle, so it's just 1/2 base times height. The base is going to be from 0 to 6, so it's going to be 6. The height now is this, and the height right here is 12, because 6 times 2 is 12, that's the function. So it's going to be 6 times 12 over 2 is what the area equals to. So we're going to get 72 over 2, which equals to 36. So graphically, we're able to check the area of this function between these intervals. Now using the fundamental theorem of calculus, we're able to do it using integration, and we got the same answer, as we should. Alright, let's go on to number 2. Now, the point of writing number 2 is, it looks just like number 1, except I changed x to t. And remember this answer, 36. Alright, so I'm going to do the same for this one now. So this one's a check. I'm going to do the same first step. I'm going to pull the 2 outside, keep my limits of integration from 0 to 6, put a t in here, and put dt. Now, the variable I'm differentiating with respect to is t. So that means that I'm integrating with respect to t. Alright, so now t is to the 1 power, so I need to add 1 to that exponent, and then with that new exponent, divide the whole thing by. So I'm going to get 2 times t squared over 2, cancel out the 2's, evaluate from 0 to 6, and we'll get t squared evaluated from 6 to 0. So it's going to be 6 squared minus 0 squared, which equals to 36. So you get the same answers when I use x. That's just to show you that the variable does not matter, as long as it's the same function. So if it's 2x plus 99, I do 2t plus 99, or 2w plus 99, it doesn't matter, because the function is the same. Only thing that matters is that the function matches the variable, and regardless of which variable you use, it comes out the same way, as long as it's the same function. Alright. So that's the point of doing this. Later on, this becomes useful when you start doing change of variables, and when you start getting into like tricky proofs, you do have to change like the variables sometimes, change from rectangular coordinates to polar coordinates. That stuff way ahead though. We don't need to worry about that for now. Just a preview of what's to come, alright?